Inspired by Joseph Liouville's foundational theorem from 1844, here we'll consider the notion of inexpensive rational numbers, ratios whose denominators are relatively small. This theme naturally leads us to the question, how well can we approximate a real number by a rational number having a denominator that is relatively modest in size? The answer to this question was given by Johann Dirichlet in 1842, and in some sense, this seminal work of Dirichlet and Liouville gave birth to the area of study now known as Diophantine Approximation. As we'll see, Dirichlet's result also offers a new definition of irrational numbers that's equivalent to the standard one we've studied earlier. We'll also describe a 19th century result of Leopold Kronecker on the integer multiples of irrational numbers. Kronecker's theorem leads to a wide array of interesting consequences, including new insights into the motion of billiard balls, planets, and why there's a power of 2 whose leftmost digits begin with your Social Security number. Well, in Lecture 19, we discovered that the rational numbers are dense on the real number line, meaning that we can find a rational number within any given small interval around any given real number. Truncating the decimal expansion of a real number is one possible way to generate a rational number that is extremely close to the given real number. Just lop off the decimal and take a look at what's there. That's rational, and it will agree for a long time with the original number. Now, of course, this method of finding rational approximations would generate fractions having enormous denominators, such as very high powers of 10, because we just move the decimal point over, and that's the power we put on the 10 in the denominator. In the previous lecture, we saw that if we consider the more refined issue of how close a rational number approximates certain real numbers in terms of the size of the rational's denominator, then we might be able to draw some additional conclusions about the number we're approximating. For example, it might be irrational or even transcendental, as we saw in the last lecture. Liouville's theorem, for example, tells us that if we have an algebraic number alpha, then any rational number that's extremely close to, but not equal to alpha, must have a relatively large denominator. Well, this result inspires a new notion, and I want to share it with you now. And this is, in some sense, my intuitive sense of this mathematical idea. Suppose that we're asked to purchase rational numbers. And those rationals have obviously a cost, and the cost is determined by the size of their denominators. The larger the denominator, the greater the cost of the rational number. A relatively so-called inexpensive rational is one with a relatively small denominator. For example, 22 over 7 is cheaper than 31 over 10. Since the first rational would cost only $7, its denominator, while the second would cost a whopping $10. Well, this leads us to an interesting question. Suppose we have a fixed amount of money in the bank. Say we have capital Q dollars, and we wish to buy a rational number that approximates a given real number A. Well, what's the best rational approximation to this number A that we can afford? In other words, how close can we get to the given number A by rational numbers whose denominators are less than or equal to capital Q? Now, notice that here we can no longer use the fact that all the rational numbers are dense in the real numbers, since the sub-collection of rational numbers having denominators that don't exceed capital Q is no longer dense. In fact, they're spread out. And we say that this subcollection is in fact called discrete. There's little spaces in between them. Well, this subtle question of approximating numbers by rationals having denominators that are not too large actually launches us into an area of number theory known as Diophantine approximation, which bookends our work on Diophantine equations. Johann Dirichlet, whom we studied earlier in our discussions of primes and arithmetic progressions, proved the first result in the area of Diophantine approximation in 1842. His result, known as Dirichlet's theorem, can be stated as follows. Let's let A be a real number and capital Q a natural number greater than 1. So let's just say that what we want to do here, before I finish the statement of the theorem, is we're going to want to approximate the number A by a rational whose denominator doesn't exceed capital Q. Well, Dirichlet says we can do exactly that. For his conclusion of his theorem is that then we can find a rational number P over Q such that the little q in the denominator is greater than or equal to 1, but less than or equal to capital Q, so we can afford it, and such that the distance between A and P over Q, which we can measure as the absolute value of A minus P over Q, is smaller than or possibly equal to 1 over the quantity capital Q plus 1 times little q. Remember, capital Q is the amount of money we have in the bank, and little q is the price of that particular rational approximation. Well, the proof of Dirichlet's theorem involves the pigeonhole principle that we've applied several times throughout our course, where if we have, for example, 6 pigeons that are to fit into 5 pigeonholes, then at least one of the holes will contain 2 or more pigeons. That's the idea. Now, to illustrate the idea of this particular proof, we'll consider an actual example, and that will actually illustrate the general principle. So let's suppose we wish to approximate the number pi, a favorite of ours, and suppose that our capital Q equals 7, which means, remember, we want to find a rational number that's really close to pi, but whose denominator is less than or equal to 7. That's our goal. Well, how do we find that rational, P over Q, that Dirichlet's theorem asserts exists? Well, first, we cut up the interval from 0 to 1. So imagine the interval from 0 to 1, and we cut it up into 8 equal-lengthed pieces. So we have 8 subintervals, and each would have length, therefore, 1/8. Okay, well, notice that if we had 9 points in the interval from 0 to 1, then by the pigeonhole principle, we would know that at least 2 of them would be in the same 1/8 length interval. In other words, the distance between those 2 points would be less than or equal to 1/8, because they would be in that same little interval, and so their distance between them would be smaller than or possibly equal to 1/8. Well, we're now going to describe the 9 points we want to consider. The 9 points will be the following 9 numbers. First of all, we'll have 0 and we'll have 1. So there are 2 of the numbers right there. And then the other ones are going to be a little bit more unusual because we're going to look at the fractional parts. Now, remember that the fractional part of a number is what we get when we lop off the integer in front of the decimal. So, 16.8, it would just be 0.8 for the fractional part. So we'll just focus on the fractional parts, and we'll look at the fractional parts of 1 times pi, 2 times pi, 3 times pi, 4 times pi, 5 times pi, 6 times pi, and 7 times pi. So notice that I'm looking at natural number multiples of pi up to 7, but I keep lopping off any integer part and just look at the little fractional part, which is a decimal number between 0 and 1. Well, so let's write these 9 numbers in their decimal expansion so we can celebrate them. Well, of course, we have 0, which I can write as 0.0000 forever. Not very interesting. And then those fractional parts can actually be computed. And I traditionally use a little curly bracket to indicate taking the fractional part. So the curly bracket of, say, 16.8 is just 0.8, just the fractional part. So the fractional part of 1 times pi, actually we know that, it's 0.14159, of course, because we know that pi is 3.14159. 14159, and we just lop off the 3. And then similarly, the fractional part of 2 times pi works out to be 0.28 something. 3 times pi works out to be 0.424 something. 4 times pi works out to be 0.566 something. 5 times pi, the fractional part, works out to be 0.707 something, and then it goes on. And then finally we get to 1, which of course is 1.0000, because there we just take 1 as it is. So by the pigeonhole principle, we know that at least 2 of these 9 numbers must be in one of these 8 intervals, each having a width an eighth, meaning that 2 of those numbers have to be a distance within 0.125, which is 1/8, from each other. Well, amazingly, in this particular example, there are only 2 numbers from this collection that are within this narrow difference. And it works out to be the fractional part of 7 times pi and then the number 1. Those 2 are actually very close together within the narrow confines that the pigeonhole principle asserts must exist. Well, if we now work out 7 times pi and forget about the fractional part, look at the entirety of that number, it works out to be 21.991148 and so on. And so what we see is, if we take a look at the difference between 7 pi minus the 21, so therefore we just take the fractional part, so 7 pi, then subtract off the integer part, so 7 pi minus 21. And then we subtract off the 1, because we're looking for the distance between the fractional part and 1. So we take the 7 pi, subtract the integer part, so it's minus 21, and then look at the difference between that and 1. In absolute value, that must be within or less than or equal to 1/8. Well, minus 21 minus 1 is actually negative 22. So in other words, we see that the absolute value of 7 pi minus 22, or the distance between 7 pi and the number 22, is less than or equal to 1/8. If we divide both sides by 7, we find that, well, pi minus 22/7 is going to be less than or equal to 1/8 times 7. Now, recall that in this example, we took the capital Q, the amount of money we're willing to spend, to be 7. And so if we write that number 8 in the denominator as capital Q plus 1, which is, 8 is in fact 7 plus 1, then we can see that we indeed have that pi minus 22 over 7 in absolute value is less than or equal to 1 over capital Q plus 1 times 7, where 7 is in fact the denominator of that rational, and notice 7 does satisfy the condition that it's less than or equal to capital Q. Well, this method allowed us to discover that 22/7 is extremely, extremely close to pi. It's an excellent approximation. It's actually within 1/8 times 7, or within 1/56 of pi, which works out to be 0.017 and so forth of pi. So very close. And this is why way back in our school days, we were told that if we have to approximate pi, we should use 22/7. Well, this exact pigeonhole principle argument can be applied in general to prove the result for an arbitrary real number a and denominator bound capital Q. So in fact, we can actually prove the theorem using this example. Well, now that we've seen that the reasoning that establishes the validity of Dirichlet's theorem, let's now consider the result itself. So let me first of all remind you what the theorem is. We've spent so much time deriving the idea of how to prove it, we might forget what it is. So the theorem says that if we have a number a, it's a real number, and we have capital Q, which is a natural number greater than 1, then we can always find a rational number p over q so that it's very close to a. The absolute value of a minus p over q is smaller than or equal to 1 over capital Q plus 1 times the denominator little q, and also that denominator little q does not exceed our bound capital Q. Well, let's now further assume that a, the number a, is an irrational number. Well, in this case, we know that for every fraction we find, p over q, the distance from a to p over q will never equal 0, right? Because if, for example, there were a rational number, let's say p over q, such that the absolute value of a minus p over q equals 0, then that would mean that a equaled p over q, which would mean that a was in fact a fraction or a rational. But we're now assuming that a is an irrational. That could never happen, and so therefore we see that the difference between alpha and any fraction can never be 0. Well, then as we let capital Q get larger and larger, and we apply Dirichlet's theorem, then we find an endless list of different rational numbers p over q satisfying Dirichlet's inequality. Well, because remember the denominator little q is always smaller than capital Q plus 1, then if we look at that upper bound of 1 over capital Q plus 1 times little q, we could actually make that larger by replacing the large capital Q plus 1 in the denominator by just little q. And so I could see that 1 over capital Q plus 1 times little q is actually smaller than 1 over little q times little q, or little q squared. Let's just make sure we see that. Notice, for example, that 2 is smaller than 3. And therefore, 1/3 in turn is smaller than 1/2. So the roles kind of swap when you take reciprocals, and that's what we're seeing here. Well, so given the new inequality, we can actually weaken the inequality in Dirichlet's theorem, because we found even a weaker upper bound, a bigger upper bound, and conclude that there exists a rational number p over q that satisfies that the distance, or the absolute value, of a minus p over q is less than 1 over little q all squared. Notice that no longer do we have that capital Q. We no longer have to reveal how much money we have in our bank accounts. Well, since our bound on the distance depends only on the denominator little q, perhaps this statement is actually easier to grasp than the stronger original theorem of Dirichlet, again, because we could toss our bank accounts away, but not too far. Well, thus, if a is an irrational real number, we have infinitely many p over q's, so therefore there exists infinitely many different rational numbers p over q that satisfy the inequality a minus p over q in absolute value is less than 1 over little q squared. In fact, the converse of this result is also true. Namely, if a is a number with the property that there exist infinitely many different rational numbers p over q satisfying the inequality a minus p over q in absolute value is smaller than 1 over q squared, then we can conclude that a itself must be irrational. This theorem actually can be proven with an application of our warm-up result in Lecture 20 that was used to inspire Liouville's theorem, although we won't take a look at that right now. Thus we come upon a Diophantine approximation definition of irrationality. A real number a is irrational if and only if there exists infinitely many different rational numbers p over q satisfying the inequality the distance from a to p over q, absolute value of a minus p over q, is smaller than 1 over q squared, or 1 over the denominator squared. Now, in many advanced applications, including proving certain numbers are, in fact, irrational, it is this definition that's extremely important. So you could see the power of Dirichlet's theorem, not only in understanding how well we can approximate numbers, but also in identifying and classifying irrational numbers. Well, let's now recall the key idea in the proof of Dirichlet's theorem. It was to consider the fractional parts of integer multiples of a. And remember that we write that curly bracket for the fractional part of a number. So for example, the curly bracket of 6.132 would just be 0.132. I just lop off the 6. The fractional part of 57.6 would be 0.6. Well, in our example that highlighted the ideas of Dirichlet's proof, we considered the first few integer multiples of the irrational number pi and then focused on their fractional parts. All those numbers must, of course, be within the range 0 to 1 because they're fractional parts. If we return to these values, we would see the list that we see, and we'd have all those values. Now, what do you notice about those values? Well, take a look at them all, and what you see is that if we plot those points on the number line, then we see that they're kind of spread fairly evenly along the line segment from 0 to 1. Not exactly evenly, but they're kind of spread out kind of evenly. In fact, if we consider the fractional parts of larger and larger integer multiples of pi, then we'd see that those values begin to fill up more and more of the little gaps between the previous or smaller multiples of pi. Well, as we consider larger and larger integer multiples, those points appear to fill up the entire interval. In other words, if we pick any 2 points between 0 and 1 really, really close together, there will be some large integer multiple of pi whose fractional part actually will lie in between those two numbers, no matter how close those two numbers are. In fact, this observation is a special case of a general principle about the fractional parts of integer multiples of any irrational number. Those values will always be dense in the number segment between 0 and 1. So on the number line between 0 and 1, the fractional parts of the integer multiples of an irrational number will be dense. Well, this result was first proved by the German mathematician Leopold Kronecker in 1884 and is now known as Kronecker's theorem. It can be stated formally as the following theorem. Let A be an irrational real number. Then the infinite sequence of fractional parts, so A, 2 times A, 3 times A, 4 times A, 5 times A, and so on, fractional parts of all those, that sequence is dense in the interval between 0 and 1. Well, I want to close this lecture by considering some applications of this result of Kronecker. Let's first consider the trajectory of an idealized billiard ball. Well, suppose we have a square, frictionless billiard table with no pockets and an idealized ball that after it's placed into motion will remain in motion forever, bouncing off the sides of the table so that the angle that the ball hits the side will actually equal the angle at which it comes off the side. So for example, here I tried to set one up here. You can see we have a square billiard table and there's no friction. So if it comes across and actually hits, the angle that it hits will equal the angle it comes off, and then it bounces against another wall. It repeats the angle. It repeats this angle. It now repeats that angle. It now repeats this angle we see here, and so on. And you can see how it's bouncing off like this. Okay, well, that's the idea. Well, as a consequence of Kronecker's theorem, there are only 2 possibilities for the path that the billiard ball makes. Either the path is periodic, which means at some points it actually gets right back on the same track it already hit, it repeats, or the path is dense on the billiard table itself. So there's 2 possibilities. Either at some point you hit here, it comes off, comes off, comes off, comes off, and notice now I'm just repeating the same thing I've already seen. So that's periodic. Or the other option is that if you start at some crazy angle, then it starts to wiggle, and it hits, and it actually essentially hits nearly every point. And so it essentially fills up space. It's dense. Well, why is this physical phenomena connected with Kronecker's theorem? Well, the path is periodic precisely when the initial slope of the path is rational, and the path is dense precisely when the initial slope of the path is irrational. So coming back to the example for a second, notice that in that example that was periodic, I actually have a slope of 1, which is a rational number, and you'll notice that after 4 moves, I'm back to where I start, and I just keep repeating. Whereas if I start with the slope that's a square root of 2, which is irrational, well, then it's not going to be obvious from my little demonstration here, but in fact, this will fill up space, which means that if I keep doing this, if I were to ink this up with a little point, I would essentially cover the entire thing. If I made my ink physically has some thickness, then the entire billiard table will be covered in black. We'd hit essentially every point. Intuitively speaking, Kroneker's result is an example of a mathematical proposition essentially implying that what is not impossible will eventually occur, no matter how improbable. As another illustration, suppose that we have a group of planets revolving around the sun at different velocities. If they all begin their orbits along the same line of sight from the sun, then Kroneker's result implies that even though the orbits will look totally out of phase for a while, at some point they will all essentially be aligned again. And actually, we can see this for ourselves. Whenever you see a pair of blinking lights, and I see this all the time, I travel a lot, and every time I travel, sometimes actually in the airplanes, they have like 2 flashlights on the bulkhead, and they each have a little red light, and they kind of blink to indicate that I guess they're charged up or something. But you can see blinking lights kind of all over the place. Well, for me, if you watch those 2 blinking lights on the front of the airplane, they look totally out of phase. But if you just keep watching them, all of a sudden, bang, they'll go off at the same time. And then they'll slowly get out of phase again, and they'll be out of phase for a while, and then all of a sudden, bang, they'll be in phase again. And that actually is a physical manifestation of Kroneker's theorem. It's kind of fun. Every time I see that, I get excited, and I hit the person next to me, and turns out they're sleeping. Well, finally, I want to close this lecture by returning to a question that I posed at the end of Lecture 2 long ago. Using Kroneker's theorem, it's now possible to prove that given any natural number, let's call it capital A, there exists a natural number, let's call it B, so that if we raise 2 to the power B and then read off its leftmost digits, they will coincide with the given natural number A exactly. In other words, given any run of digits, there always exists a power of 2 that begins with that run. So there's a power of 2 that begins with your Social Security number. But don't tell me what it is, because you're not supposed to tell. Okay, so how can we make this surprising assertion believable? Well, we first consider the logarithm of 2 to the b power. Now, by properties of logarithms, it follows that the log of 2 to the b is actually equal to b multiplied by the log of 2. That's an identity from properties of logarithms. So in other words, log of 2 to the b is actually an integer multiple of log 2, namely b times log 2. We now recall from lecture 19 that we proved that log of 2 is an irrational number. Therefore, we can apply Kroneker's theorem to conclude that the fractional parts of integer multiples of log 2 are dense on the interval between 0 and 1. And it is this density property that allows us to find the correct exponent b for which 2 to the b is close to the given list of digits that make up A. And close in this case means that they agree from the leftmost spot onward. Kroneker's theorem and more generally how it came from, Dirichlet's theorem, are important results that show us how irrationals fill up space in a variety of different ways. The theorem of Dirichlet tells us that given any real number, in fact, we can always find an affordable rational nearby. And Kroneker's theorem tells us if we take a look at the integer multiples of an irrational number and just look at the fractional parts, we'll see something that essentially fills up all the number line from 0 to 1. Welcome to the world of Diophantine approximation.